Hello everybody, we're going to do one more topic on some applications of integration and going to include arc length and surface area. So the first question we have is a problem. If we're given a curve, a continuous curve in the plane, how do we find its length? Well, one way to start, of course, is to go back to what we remember about our distance formula between 2 points in the plane. That is, if we're given 2 points, x1, y1, and x2, y2 in the plane, you recall that the distance is essentially using our Pythagorean theorem for the distance between the x values plus the distance between the y values squared. So what would we do? Well, on what we call a rectifiable, continuous and differentiable curve on an interval from A to B, we can approximate the arc length as follows. Now, by the way, when we say rectifiable, what we mean is that the arc length is continuously connected at every point. There's no points that it skips. It doesn't do any weird stuff like come to a point and then have an undefined differential and so on. So we're going to have a rectifiable, continuous, and differentiable curve on this interval. Well, one approximation, of course, would just simply be to take a straight line and estimate what would that curve be. We know it's got to be longer if it's curved away from this line from the point from A to B. That's one estimate. But of course, as we've done in the past with other integral type values, we know that we could divide up this area into smaller intervals and then use our distance formula. So we need a good way of doing that. And simply using the distance formula between each point along the curve is going to prove pretty difficult. So here's a way to think about this length. Let's take the length right here along this line segment. And that length is going to be equal to the square root of the distance between our x's, right? So that's b minus a quantity squared plus the difference in our y values, right? So we're going to take f of b, whatever it is, minus f of a, r is our y value, and square that integral, square that difference. Well, that's actually sort of an interesting description, because what we could do is that means that we could rewrite our integral just a little bit. Let me show you how. I can factor out the quantity b minus a squared. So I'm going to have b minus a times the square root of the quantity 1 plus, and let's divide. We're going to get a quantity that looks like this: f of b minus f of a, that's a b with a parenthesis around it, there we go, over b minus a quantity squared. Well, what could we say about that? Well, it's sort of an interesting notion right here, because this quantity should look maybe a little bit familiar to you, in that you recognize that when we have 2 points on a curve, we can say by the mean value theorem that there is at least one point C such that the derivative at that point C is equal to the limit. Well, it doesn't even have to equal a limit here, right? Is equal to, I'll go back to my pen, is equal to f of b minus f of a over b minus a, right? So in other words, writing this quantity right here means that we could actually state that if we had 2 points within an interval, we should be able to say something to the effect that if we were to take, actually, what am I doing it up there? If we were to take this quantity right here, we could state that our length is something like a quantity b minus a times the square root of 1 plus some point c in that interval, f prime of c, squared, right? So somewhere within this interval from A to B, we could say that there's at least one point C such that the line of the tangent at C is equal to the line of the secant line through that. All right, so how does that affect us here? Well, let's think about dividing up this distance now, not as a major value A to B, but in between any pairs of small changes in x along the interval. What could we say about that? Well, in this case, what that means to us is that if we were to pick some small intervals I in this set of points right here. So we've got x of I minus 1 over to x of I. Right? What would we say? Well, somewhere between x of I and x of I minus 1, there's going to be some point C of I, such that the slope of the line tangent to the curve through those points will be equal to the slope of the line secant to the curve through those points. And so what we could say is that by our mean value theorem right here, right, again, right, f prime at some point C sub I is equal to f at x of I minus f of x of I minus 1 for any of those pairs I and I minus 1 within our interval from A to B over x of I minus x of I minus 1. And so if we call each of these changes delta x right here, what we can really say is that the total length of this curve will be the same as if we were to have taken the sum from I equals 1 to n of each delta x times the square root of 1 plus the derivative f prime for each point C sub I in that interval squared, right? Based on what we just said about our mean value theorem, that must be true. So, like many things that we do in calculus, what are we going to do? Well, in calculus, when we came across a summation that represented a sum of areas, or in this case, arc length estimates, for our intervals from x sub 0 all the way up to x of n for each x of I, what we did was that we took a limit. And if we take this limit, what's going to happen? Well, sure enough, we're going to get an integral. And the integral goes like this. If we take the limit as n tends to infinity of x1 plus f of x, f prime of x of I, instead of c sub I right here, same idea, delta x, as those intervals tend to get infinitely small, we get the integral from a to b of the square root of 1 plus the derivative f prime of x squared, d of x. Well, there we go. There's our formula right there that we're going to need.